Good evening. My name is Chia Vang. I am a professor of history, and I'm also the interim chief diversity officer for the UW-Milwaukee campus. I would like to welcome you to the first of a new series, Asia in Conversations, that we are created here at UWM. This series is intended to showcase the academic and social significance of the creative work by Asians at UWM in the science, social science, the arts, and humanities. It will take the shape of informal but not casual, as you will see tonight, conversations between UWM faculty, researchers, and their interlocutors in the wider world. So this series is sponsored by the William F. Vilas Trust, the Global Inclusion and Engagement Division, and the College of Engineering and Applied Science. I thank Professors Kumkum Sangari and Shin Huan for serving on the planning committee. We are so thrilled to share the work that our Asian faculty and staff are doing on this campus and how its applications in the wider world is making such significant impact in the US and across the globe. So tonight, we thank Professors Pradeep, Rohatgi, and David Weiss for beginning this conversation. So we hope that you will enjoy, and I hope that you will have some conversations among yourself, come up with some questions so that when they are done having their conversation, we want to engage you as well. So please feel free to take time to write down some questions as you listen to how they came to do the work that they do now and what significance has the research that Professor Rahaji has done, how has it had an impact in the state of Wisconsin in particular for our conversation tonight, but globally as well. So what I will do is they have very long biographies, but what I will try to share with you a little bit about their background. Some of you know them, many do not know them, but we are going to share a little bit about their background. So I'll begin with Professor Pradeep Rahaji. And again, he's one of my role models. I feel so blessed to know him since I've been at UWM. So it's long, so please be patient because you need to understand Professor Rahaji's accomplishments to understand why he's beginning this conversation with us. So Pradeep Rahaji received undergraduate degree from Indian Institute of Technology in 1961 and a doctorate from MIT in 1964. He served as a professor at the Indian Institute of Science in Bangalore and Indian Institute of Technology in Kanpur after working in industry. He then served as the founder, director, and CEO of two national CSIR laboratories in India, National Institute of Interdisciplinary Science and Technology, Trivandrum, and Advanced Materials Research and Processing Institute in Bhopal. He has served as Ford Briggs and Stratton Professor and State of Wisconsin Distinguished Professor, and currently serves as a UW Distinguished Professor and Director of the UWM Centers for Composites and Advanced Materials Manufacturing at the University of Wisconsin-Milwaukee. He has co-authored over 350 scientific research papers, 70 papers on science and society, and has 20 US patents. His initial research on cast metal composites has been listed as a major landmark in 11,000-year history of metal casting by AFS, and TMS organized a Rohatgi Honorary Symposium on cast metal metrics composites. He has developed new lightweight composite materials, including those made with plant-based materials and waste byproducts to conserve the environment. He has served on several committees of governments of the United States and India. Currently, he serves as the node leader for the NNMI DOE Remade Institute in the US to reduce embodied energy in materials and promote circular economy. He has been a member of the Milwaukee Ethnic Council, World Future Society, Hindu Temple, and interacted with Metropolitan Milwaukee Chamber of Commerce. He has provided consulting services to a large number of private corporations on manufacturing and to the United Nations and the World Bank on technology policy for sustainability in the developing world. He serves as the Chief Technology Officer of Intelligent Composites LLC at UWM, which is a UWM startup to manufacture metal composite for industry. He is also the recipient of numerous awards for excellence in research from all over the world, including Hall Herald and Scientific Merit Awards by American Founderman Society, ESM Milwaukee Award, Honorary Medal for Motor Transport Institute in Poland, ASME Research Award in Tribology, Chalmers Award for Materials Processing from TMS, IAAM Scientist Award in Sweden. He is a fellow of ASM International in the USA, uh, Institute of Materials in London, Indian Institute of Metals, India, American Association for Advancement of Arts and Sciences, the World Academy of Science in Italy, Wisconsin Academy of Science and Arts, American Society of Mechanical Engineers in the USA, Society of Automotive Engineers in the USA, Society of Manufacturing Engineers, the Minerals, Metals, and Materials Society, and the Society of Automotive Engineers in the USA as well. And finally, Materials Research Society in the US and the National Academy of Inventors. Now, to be the welcome that you have to be able to read this wonderful bio, so thank you for sharing your wonderful bio with us. And our second speaker is a friend and colleague of Professor Rohatgi, is Mr. David Weiss. Mr. David Weiss is Vice President of Research and Development for ECK Industries, Inc., and CEO of Intelligent Composites, and he has developed processes to produce many types of aluminum metal matrix composites, including hybrid, multi-component systems over the past 30 years. Weiss has authored over 80 papers on the processing and application of aluminum, metal matrix composite, and magnesium castings. He has won numerous industry awards, including the John A. Penton Gold Medal from the American Foundry Society for pioneering work in the premium aluminum casting industry. He holds 7 patents, including 3 for the development of the ALCE alloy system, and is leading worldwide commercialization efforts in aluminum, metal matrix composites, and ALCE alloys. So thank you so much. That was a lot. And just reading the bio, I already need a dictionary, just so you know, as a historian, as someone in the humanities, I need a dictionary, but I'm so thrilled and so blessed to be in your presence tonight, even though we're not in person. I want to turn it over to the two of you to have a conversation about how you came to know each other, how you do the work that you do, and how you continue to engage with each other to benefit society. So I'll turn it over to Professor Rohatgi and Mr. David Weiss.
Thank you so much for organizing this meeting. And I think David and I met, I really don't remember exactly, but one day he showed up in my lab and said, I'm interested in metal composites. And since then, we have been partners in crime in promoting research in this field. So I'll let David ask the first question, because he always wants to be ahead of me.
Okay, thank you, Pradeep. It would be helpful for the audience, I think, to try to define what are metal matrix composites and how do they help save energy and what are they good for?
These days, global warming has become one of the most important problems, and to conserve energy and to reduce emissions has become a very high priority. And what metal composites do, it allows you to make transportation components lighter. Means your cars will be much lighter. They used to be made of steel. Increasingly, they are made out of aluminum and aluminum composites. So you consume less fuel in going the same distance, and you have less pollution that is given out of the car. So that's one of the major applications, and this has applicability not only in cars but in scooters, in motorcycles, in trucks, trains, airplanes, and whatever you have, anything that moves. That's one of the major applications. The second way it saves energy, take for instance aluminum. It is one of the largest energy consuming materials in its manufacture, and if you put some things in it like ceramics, which consume less energy, you reduce the embodied energy of aluminum. So the composites by themselves have less energy to make them, and then they save energy when you put them in transportation systems. So these are this is one way that it is trying to help prevent global warming.
Thanks, Pradeep.
Yeah, go ahead.
No, your question.
Well, David, when did you get interested in manufacture of lightweight materials, including metal composites to conserve energy? You have been my
So
biggest partner in crime, if you may say so.
yeah, so Eck Industries, by way of background, we are a founder in Manitowoc, Wisconsin, founded in 1948. And what we have always done is we have produced structural components, components that take load as opposed to things like covers that are just some sort of covering for a device, but where there are real stresses and loads on the part. And as part of that business, we had routinely worked with customers to convert from heavier materials to lightweight aluminum alloys. And you know, as we came to learn, it's not all about strength, because oftentimes uh, uh, you know, strength will be higher in an aluminum alloy actually than in an iron alloy if you choose the right alloy, but very much about stiffness. And so oftentimes a significant amount of weight in an aluminum casting is taken up by ribbing in order to give it some geometrical stiffness. And so when I saw a notice about Dr. Rohatgi talking about metal matrix composites, and did some of my own research before that lecture, I saw that one of the benefits of it is to increase the stiffness of an aluminum alloy. And this was of great interest to me. And so I went to the lecture. As Pradeep says, I showed up in his lab. We exchanged information, and we have been friends and colleagues ever since for certainly more than 30 years. I don't remember exactly when, but it seems like a long time. And have been working on various composite systems and working to make those systems manufacturable in the environment. Because we didn't want to just do laboratory work. We wanted to move a lot of that laboratory work that he had pioneered into a production foundry. Pradeep, you came to the University of Wisconsin and had done some work academically prior to that. Can you tell us a little bit about, you know, where you started with in composites?
Well, it's a long story. When I did my PhD thesis on freezing of water, because I was concerned about availability of water. I grew up in a town where water supply would be turned off very often. So I picked up freezing of water for my PhD thesis because I thought this will solve the problems of water all over the world. And at that time, I ran into a thesis where somebody was throwing some sand in water. And I said, why is he doing that? And this was related to trying to make ice stronger and stiffer for the planes to land in Alaska. They had some landing strips in Alaska, and the planes would land many times, and then the ice runway would break, and so on. So this gentleman was adding dust or sand to water to make it stiffer, to make the solidified ice stiffer, and that gave me a thought that, you know, that stayed in my mind. It had nothing to do with aluminum at that time. And then when I started to work with International Nickel Company, people from General Motors came one day and they said, look, the cars have a lot of cast iron, which works wonderfully well, but it's very heavy. Can you do something to make aluminum and use it in place of cast iron? And cast iron has graphite in it. And then I said, well, if I could add some graphite to aluminum, it will become lighter. And if you look at the thermodynamics, I'm not going to get into the science. It's not possible to dissolve any graphite or carbon in aluminum. And that's when I remembered my reading this paper many years ago as a graduate student, that if you throw something in a liquid and then freeze it, it becomes stronger. I want to mention this because how something you read and forget about it comes and triggers. So that's when I developed the technology to mix graphite particles in aluminum melts and to freeze it. So the graphite is encaptured or it is encapsulated in aluminum. Just like you wanted to make dusty ice when you're trying to make an ice cube, put some dust in water and put it in the ice tray in your refrigerator. You will have an ice cube that you don't want to put in your drink, but it'll be stronger and stiffer and so on. So that's where I discovered when I was at International Nickel Company in response. And we did some lab trials, we did some component testing, and it looked very good that it could help reduce the weight of transportation systems. And then it could conserve energy and it could conserve the environment. At that time, the company I was working said, let now General Motors do the rest of the work. We will stop working in this area. And at that point, I returned back to India and carried on my work at the Indian Institute of Technology and Indian Institute of Science. And then I was asked to develop 2 large national labs, which allowed me very large support to continue this work. So I've stayed with that work. I've done other things, but this has been my mainstay to develop materials that will conserve energy and environment. And in addition to metal composites, I have done other work on incorporating plant-based materials, like fibers from coconut fibers and banana fibers to make composites, because now I'm using a renewable resource to make stiffer materials. I was at some time called that I've gone coconuts and bananas, and I even put some coconut shell char in aluminum to make it lighter. So that has been my story, that driven by a passion to somehow help with energy conservation and environment to develop new materials. That's what I have done all these years. And then I came to UW-Milwaukee in '85 after surviving the infamous Bhopal accident. We were happily settled there and carrying our work, but that kind of made life a bit uncertain in that city. And I and my wife and kids wanted to get away from the toxic gas for a while, and we came here to UW-Milwaukee to start this work, and have been here since then. And I met friends like you who were interested in it, and the great foundry industry in Wisconsin that were willing to try my ideas on an industrial scale. So that's how I got into it and have been in this business. And if you remember, David, I and you just co-authored a paper on 50 years history of cast metal matrix composites, which was presented a year ago at the American Foundry Society. So that has been my story with metal composites, and at the University of Wisconsin. It was a very good place for me to work, because Wisconsin is a state with the largest number of foundries in the United States. And they allowed me to do work in the lab and allowed me to try out my ideas on industrial scale in the industry. And people like David have started manufacturing prototypes and parts of this, which I could never have done in a university laboratory. So David, it's your turn.
Yes.
I'm going to ask you a question. What do you see as the future of metal matrix composites in Wisconsin and around the world? And also, what have been some of the current uses of metal matrix composites, and what do you see as future uses?
So that's a big question, and I'll try to be concise in answering it. If in today's world, the largest use of metal matrix composites in general is in thermal management. A lot of composites, particularly based upon those with silicon carbide, have a much reduced coefficient of thermal expansion versus regular aluminum or other materials. And so they're widely used for cooling and mounting chips in applications as diverse as from an iPhone to controllers in automobiles. There's a lot of composites in automobiles, but most of them are captured in the brains or the computer section of the material of the engine, trying to control the engine. So it has found a very big role in thermal management currently. It has found quite a few applications in space. Again, because of the thermal properties of the material, you can go from the bathed in sunlight to bathed in darkness with big temperature differences, and you can get structures that are held together. What we've tried to do, and we've tried to do together for a number of years, is to penetrate the automotive market with composites in a larger way. Our company did the brake rotors for the Plymouth Prowler, for example, way back in 2002, 2003. There's been a lot of work with composite pistons and other applications in the internal in a typical automobile, both within the engine and as part of body structure. One of the issues has been the fact that an aluminum-based MMC is more expensive than an iron component. It's more difficult to machine, and people aren't that used to it. And so people are still trying to understand how they can use them and how they can incorporate them into their new designs. There are some new openings with electric vehicles where the battery packs are so heavy, and even and so weight reduction is even more important in those kind of applications. And so obvious applications still remain brake rotors, and brakes don't have to work as hard in electric vehicles because of partial electrical braking. And so that would be good. But there's always been a cost hurdle, and people need to work through that and understand how to design with the materials.
If I may add to what David said, it was an interesting story. We developed it for lightweight for transportation, but as David said, the biggest applications have been at this time in thermal management, in computers and so on. In addition, they have been used, I mean, in the antenna in the Hubble telescope, that was made out of an aluminum carbon and then aluminum silicon carbide composite. The struts of the space shuttle orbiter, they were made out of aluminum boron. And in many aircraft applications, it has in fighter jets, F-15 planes, and helicopters. So it has worked in transportation systems, in heat management, as well as recreation. Several mountain bikes have used aluminum silicon carbide because they are lighter. So it has found applications in recreation equipment, in golf clubs and mountain bikes as well.
I happen to have a composite golf club, and I can let you know it has not improved my game a bit, but I don't blame the material at all for that.
Not to be blamed, but your game is bad.
Yeah, my game is just bad. And I'll add further, I think that in automotive applications seem to be in the past and the future. We had the rotors on the Prowler were a huge technical success. As a matter of fact, as is the case when cars are no longer in production, companies will order components based upon how they believe that they need to be replaced in the vehicles, and they ordered a batch of rotors. And keep in mind, this car came out in 2002, and they've barely dented that batch of rotors because the rotors effectively last forever. The aluminum rotors last forever. So there's been a lot of successes in the past. There remains a lot of interest in the future. But structural components where people have been more concentrated on cost has hindered a little bit the composites in the automobile industry. But I think that's changing. We've seen a new surge of interest and are talking with a number of people for a number of automotive applications. Pradeep, if I can, I'd like to ask you a question about your role in the Foundry Educational Foundation as a key professor, and some of the benefits that you see to UWM and the state and the industries in Wisconsin.
When I came to UW-Milwaukee, as I said, Wisconsin was one of the largest states in Foundry, and the only Foundry Education Foundation school was Madison. So I said, well, we should start the same program here. It took a while. There was some resistance, but finally I was able to start what we call a Foundry Education Foundation program that's funded by Foundry industry, and 21 schools, excuse me, 21 schools across US are accredited and or certified now, and we are one of them. And in this program, the foundation gives money to have a education program at a university. So over the years, about 200 students at UWM have received FEF scholarships. In addition, the foundation helps the students find jobs. They are interviewed by industry, and I believe about 60 students from UWM have found jobs in Wisconsin foundries. In addition to that, they have found jobs in companies like Boeing, Intel, Tesla, and Apple. So excuse me, the program has allowed our students to find jobs, scholarships, and the foundation has also helped me in build our lab at the university.
I wanted to make an additional point, and this is not, I guess, directly related to the Foundry Educational Foundation, but UWM has an industrial advisory board for that I believe is associated actually with the Foundry Educational Foundation. But UWM was one of the first to have a very robust industrial advisory board with foundries and suppliers to the foundry industry and software suppliers to the foundry industry. And actually, the model at UWM is now being emulated by other companies because for some general reasons, the universities are being asked to do work that is more relevant to industries. And so you will see a lot of actually well-known industries that have never had an industrial advisory board try to put together industrial advisory boards to guide research. And so UWM was kind of a pioneer in that regard, and other people are starting to follow suit because it is really necessary to try to match research to some of what the industry requires. I'm a big believer in pure science, but there has to be some applied science as well. That is part of it.
David, I'd like to, since this meeting is arranged as a conversation with Asia, I'd like to share that how the synergism between United States and Asia has helped the growth of this field. As I mentioned that when I had initially done this work in US, they said we will no longer work in this area because let the automotive companies do that. So I went to India, and I must say that they provided me with enormous unlimited support. In Asia, at least until recently, you never had to write grant proposals to do research. Government gave a lot of money to do research. And I did a lot of these developments that I did were done in India. And I thank the Institutes of Science and Technology, as well as the Council of Scientific and Industrial Research. And when I moved here, all that knowledge base moved with me to United States. And then here I was able to get the benefit of getting inputs from industry, people like David Weiss, who kind of helped me direct that work so that it will become industrially relevant. So here is an example that a invention that was made here in the United States went and grew for a while in Asia, and then came back to this country. And if I am going to invite David in a minute, that the reducing energy consumption in transportation, it is a bigger imperative in Asia at this time than US, because if you look at it, the fuel costs are much higher in Asia compared to US. The pollution because of transportation is much higher in Asia. India itself has 22 out of 30 most polluted cities, mainly because of transportation. So this is an example that how work done in US and in Asia, they synergistically support it. And I'm going to ask David, because David has been to both China and India to talk about what he sees as the potential of these things in India and in China and other places in Asia.
Yeah, thanks, Pradeep. There's a real interest, obviously, in both countries. Both countries face similar challenges, and really all of the countries in Asia, I'm going to say, face similar challenges. You have relatively high population density in places. The burning of fuel causes pollution, and so there is certainly a drive to improve energy efficiency, to clean up the environment. They are very, very serious about doing that, and continue to look and support industries that want to help the government to do that. It has surprised me a little bit, but you and I both watch the literature on metal matrix composites, I'm sure. And these days, probably 9 out of 10 papers on metal matrix composites are coming out of Asia, as opposed to the US and Europe. So they are aggressively trying to understand these materials better, understand how to process them better, and get them into applications as soon as they can. The foundational work has been done, but getting them into production, there's obviously a push in Asia to get that done as rapidly as possible, because the students are being supported, the research institutes are being supported in order to continue to develop these materials into truly production materials.
I might add that when I moved here, General Motors visited UWM, and they said, well, we see that the Business Associate reports indicates that India is #1 in research in metal matrix composites. So that's what David is saying, that the intensity of research in India, China, and other countries in Asia has been much more. The government has funded this research much more than in the US. So the point I'm trying to make, that there is a lot of synergism, and it could be that these things may be used in Asia in the beginning in larger larger amounts, and then they will come back to US.
Yeah, I believe that that's what'll happen. You know, one of the byproducts of having all this research done is, right, you have a lot of students involved. Those students go to um, the big manufacturing operations in Asia, and they have some understanding of metal matrix composites. So they will be able to help to ease the path of getting new materials into vehicles or other structural applications, I think, which is very, very important. And you know, that may indeed give the US a push to look at them more seriously or in greater depth than they're currently doing.
David, can you talk about Intelligent Composites, a startup that was UWM technology that you are now serving as the CEO?
Yes, we have a company that is looking to commercialize a hybrid composite, which is a composite containing both hard particles and a lubricant in that. In a typical internal combustion engine, most of the frictional losses incur in the engine, and more than half of those frictional losses occur between the piston rings and the liners. Putting lubricant in the liner material can reduce the coefficient of friction, therefore improving efficiency and fuel economy. We, in smaller output engines, and Dr. Rohatgi has demonstrated this in some of his earlier work, in smaller engines, if you have an effective amount of lubricant that is cast into the liner, you can run, for example, a two-stroke snowmobile engine or a lawnmower engine actually without oil and not have it seize up, because the lubricant is throughout the cast structure. And unlike coatings which wear away over time, as the liner wears, which occurs very slowly, you simply expose more graphite in this case as a lubricant. So this is a powerful way to reduce emissions, improve fuel economy, and reduce weight in internal combustion engines. And we have a number of large customers who are interested and are working with us to further develop this technology. The other thing that we're interested in doing as well is making multi-material structures which are part composite and part just traditional aluminum alloys, because composites can be more difficult to machine. Being able to do a multi-material structure can be very important, and again, offer significant advantages in component stiffness and weight. And so Intelligent Composites was set up to exploit those technologies to kind of drive them into the marketplace, to understand whether they could be leveraged into a business. Pradeep, I'm kind of fascinated, and actually I'd like to hear a little bit more about some of your work in self-healing and self-cleaning alloys. This is really a brand new field in metals. There's been a fair amount of work in polymers and that kind of thing, but I'd like, and I'm sure the audience would like, to hear a little bit about some of your revolutionary work in self-healing materials.
You know, if you look at a human body, it is one of the best assembly of materials that you can ever imagine. You break a bone and it heals. You just put it together and it heals. If you have a cut in your skin, it heals. And this always fascinated me, and I was always saying that, can I teach this trick of healing in biological materials to man-made materials? And I started again to ask, what can I do this with metals? So we have developed self-healing metal matrix composites, where if you, because you have applied too much load, there is a crack that has formed. Up to now, if a crack that has formed in a metal extends until the material structure fails. In glass, it happens very quickly. You drop the glass and it fails. Metal is more malleable, so it takes longer time for the crack to grow, but it does fail. So up till now, up until recently, if there was a crack, you knew that sooner or later the metal will fail. So we have developed composites where after a crack is formed, it can be healed just like in a human body. And this is accomplished by incorporating shape memory alloy wires. Shape memory alloy remembers its shape. You can take a wire and crumple it up in any way and just throw it in boiling water and it becomes straight again. So it remembers its shape. And what we did was we put this in aluminum. When we stretched it to the point where aluminum broke, there were cracks in it. All we did was put it on a hot plate and the wire shrank, the shape memory wire shrank, and it closed the gap and the crack was healed. So this was one method of creating self-healing materials. The other is you will incorporate micro balloons. Your skin gets healed because liquid goes there and seals the scab and forms a scab. So we developed techniques to incorporate hollow microtubes or hollow micro balloons in metals. They were filled with liquids or solids that will become liquid by heating it to a high temperature. So if there was a crack in a metal, that crack will break open the micro balloon or micro tube, and the healing liquid will flow into the crack and will become solid by cooling. So these were two techniques of self-healing metals that students in my lab have developed, and we have a lot of fun showing that you can take a sample of this material which is straight, you can bend it until it cracks, you put it on a hot plate, it becomes straight. That means it remembers its shape. So it recovers in shape, and also because it is on a hot plate, the crack is repaired, it joins itself. So these are examples of self-healing metals, and I'm very excited about it. A lot of students of mine from the biomedical engineering department are now looking at it, that how some of these self-healing materials can be used for biomedical applications. But the implications are large. If you have a Mars rover and there is a crack in a part, you can't send a mechanic easily up to Mars. You need to teach them self-healing. In airplanes, if there is a crack, you want to make sure you can repair while the plane is in flight. I've also done some work in water area, as David mentioned, that many times water likes to stick to metals because of the high surface energy relationships. So what we have developed self-cleaning metal composites, where if you put a drop of water, it just rolls off. And in rolling so, it takes away any dirt. And the other application of self-cleaning materials is that when you pump water through a pipe, it will consume less energy because there is no wetting between the water and the pipe. So there's a lot of excitement these days how to reduce energy consumption in pumping water. So that's where self-cleaning materials, they can reduce the drag energy when you pump water, and also it will prevent corrosion. Corrosion causes major losses of materials. So self-cleaning materials can reduce corrosion and reduce all the losses. And when you combine self-healing and self-cleaning in a pipe, first of all, it will consume less energy. And if because of a puncture, the water starts to leak, the self-healing kicks in and it could close the cap. So you will reduce loss of water due to failure of the pipes. So these I'm very excited about self-healing and self-cleaning materials because they have many applications beyond transportation or thermal management.
Yeah, it's really difficult to overstate the potential importance of parts that never fail or don't fail or fail it takes an order of magnitude longer in time for them to eventually fail. So this is great work, and we hope to help you bring this into customers' parts as we move down the road here.
I might share something that one of the things David said earlier, that one of the barriers why this metal composites industry has not taken off and is in every car, every scooter, every motorcycle or every truck. The problem has been the cost. So every time the General Motors or other automotive companies will tell me how to bring the cost down, and I got tired of listening to this story. Then we developed something, since the talk is about conserving energy and environment. I developed utilization of waste fly ash into aluminum. Fly ash is one of the biggest waste byproducts in United States and all over the world. About 80 million tons of fly ash is generated because of burning coal to generate electricity. And it is very much landfilled. There's some use in building materials, but mostly it is landfilled, and it ruins the underground water supply. So what was very happy to do the work, I developed utilizing or incorporation of waste fly ash in metals. So this was a win-win situation. You took a waste byproduct that was polluting the environment and you added it to aluminum. So it displaced energy intensive aluminum, and you produced a part that was much lighter than steel. So here is a situation where where there is utilization of something that was harming the environment to conserve energy in a metal, and that it goes further to save energy. And we discovered that this waste fly ash, which somebody actually pays you to take it from their plants, 2% of these were hollow micro balloons, perfectly hollow spheres. It will take you a lot of money to make one micro balloon, but here they were available to you for free. And then we harvested these micro balloons and put it in metals to make self-healing metals, or to produce materials that absorb a lot more energy. Army was very interested in these being a very lightweight armor instead of steel armor. My work has been supported by Electric Power Research Institute. They supported the work on adding fly ash to aluminum. This work actually was started in India with by one of my students. When it came here, it grew very large here. And Army has been interested in this because they want military trucks. People like Oshkosh, they want them to be lighter, so military trucks and tanks can be airlifted. So there's been a lot of interest from Army Research Lab, and Tank and Automotive Command have funded the work at UWM. In addition, of course, to the National Science Foundation, Department of Energy, and Office of Naval Research, they have funded my work, in addition to companies like General Motors, Ford Motor Company, and a lot of water companies, water equipment manufacturers like A.O. Smith and so on. I would like to talk, as I said, that I always in my life, I've tried to do double barrel problems that had scientific challenges, as well as they should have some use, immediate use to the society. And that's why I'm so happy that I have a chance to serve as a node leader for materials manufacture in the DOE Remade Institute. They came to me because they saw that UWM was developing materials that conserved energy in their manufacture and use. And this institute is geared to increase increase recycling of material. So you don't have to dig stuff from the ground and make material that takes a lot of time. Can you recycle the plastics that is in your garbage collection? Can you recycle aluminum that is wasted to make new aluminum components? Can you reuse paper rather than throw away paper? So that's one area and UWM is involved in it, and I'm involved, and we are very happy that this is another activity at UW-Milwaukee that is going to benefit in terms of conserving the environment and reducing energy to manufacture materials and to use materials. David, your turn.
Is it my turn to ask a question?
You always give me a hard time.
Okay. One of there's, it's safe to say that there's some politics between the U.S. and a number of Asian countries. So what's the role that a university has in trying to build the bridges between the research communities, widely separated research communities?
I think you ask a very, very good question. We, of course, at the university try to be as much apolitical as we can. As you have been to my lab and many university labs, we are very fortunate that we have students from all over the world that come, including Asia. And they learn the science, they learn the technology. Some of them, of course, stay on here, but many go back. And I think these personal relationships are very, very valuable between Asia and the US, because they transcend what's happening in politics. And they inform each other of the work they are doing. Together, they work on getting these materials used in industries. So I see a tremendous role of universities in bringing the scientists and engineers of the two countries together, despite what is happening at the political level. And as I mentioned earlier, that it could be that the invention done here will benefit Asia more than it will benefit the United States, because the energy costs are much higher and the pollution is much more. So I see a major role, and one of the best things I feel when I go to my lab, that I have people from all over the world and they are rubbing shoulders, and they develop friendships that last their lifetimes. And I wish their friendships dominate the environment in the world more than the conflicts between politicians. I see a future where the relationships between scientists and artists and sports people, they dominate the world rather than the relationships between politics, which often are very confrontative. I wish I could figure out a way to run the world without politicians, or without the role of politics. At least it should be diminished.
So Dr. Rohatgi for president, right?
No. I said that we want a world where the role of politicians is reduced. I would like to see a countries and world without any presidents, where the scientists and politicians and artists and poets, they run the world, not so much the politicians. I know it's not easy, it may never be possible, but it's something we should think, because I do worry. I see how much time they waste in making sure that their party wins and the other party loses. And instead of that, all of that energy can be spent in developing new products, developing new healthcare solutions. So that's where I think the role of the university is very important. It brings people from all over the world and develops people-to-people relationships that last all their lifetimes. And they can then go back. They can then go back and influence their governments. Many of the leaders across the world are graduates of US universities. And I'm sure that relationship and that memories that they have spent time here, that will prevent confrontation between their countries and US and between those countries. So that's another major thing, that US has been a major cradle for education of world leaders all over the world, particularly in Asia. And that would help with much better relationships between US and the rest of the world.
Uh, Pradeep, I want to ask you another question. You and I and Eck Industries have worked together for a lot of years. You're also working with some other industries in the state as well. I'm wondering if you could share that information with the audience, because I think it's important.
Yeah, as I mentioned, that Wisconsin proved to be a very good place to continue my work in metal composites, because it is one of the largest metals manufacturing states with the largest number of foundries of any state. And this has allowed me to, in many ways, in our business and engineering, we like to see that our processes that we develop in the lab, they can be tried on a large scale. And so many industries have opened their doors for me to try out my crazy ideas on a large scale, including Eck Industries and David. And that has proven a big help, that our ideas can be upscaled, they can be converted into products on a large industrial scale. The other thing that I found very useful here, like I have worked with Oshkosh Truck for many years. One of my students joined them, and since then the relationship grew. And we have worked a great deal for developing lightweight, as I mentioned, lightweight military trucks, lightweight components for their tanks, so that they can be airlifted. And the relationship with Oshkosh then led to a very large research funding from organizations like Tank and Automotive Command and Army Research Lab, because they saw bigger applications of these things. So here is an example. And I have worked with many industries, including Amalga Composites, A.O. Smith, where we have worked together to bring a lot of external federal funding, which is only given to an industry university consortium. Like at Intelligent Composites, we got a STTR grant from NSF to do research. So the relationship with industries in Wisconsin has helped me bring a lot of research money, which would otherwise not have come to either the university or the industry by itself. It has really been a great relationship, and industries have given a lot of help to us. David knows if my student needs a material, I just call him, and next day, I see David in my lab with the material in trunk. So they have given us materials, they have given us supplies, and they have served as guest lecturers. In my class, I like to bring the education that is learned on industrial floors. David has talked to my students, and so have many other industry executives in Wisconsin. And that enriches the experience of my students in my class. So it has been a great relationship. I don't think I could have done this in any other state where the metals industry was not so strong. And as I said, they have hired my students, which is a very good thing. And I think it's because of the industry that we have this Foundry Education Foundation program. They recommend to the industry group that this program should be grown at UW-Milwaukee. So it has been a very good ride. And as I said, I look forward to being some use to the local industry in return for all the help they have gotten. We have been able to provide trained manpower, which is very good, because they look for people who have expertise in the area that they are manufacturing. So we have been able to give a little bit back by providing them with trained manpower and providing them with the research background that they may not have had in-house. So it has been a great relationship, and I feel very good as part of a university which has had a big impact on the state of Wisconsin in terms of promoting industry, increasing competitiveness, of local industry and providing trained manpower to the local industry.
Thanks. I think we're getting kind of a red light here that the moderators would like to open up to other questions and comments.
Yeah, so thank you so much for the conversation. I just want to say that for those who just joined us, please feel free to post your question to all of us on the chat, or you may unmute yourself and ask the questions directly. I just want to say for the last hour, I have learned so much, and I think, you know, Professor Rohatgi, there is tremendous impact that your research has had on industry and on society, both here and around the globe. And I'm so pleased to see the relationship you have with, you know, Mr. Weiss and Ec Industries, and the contributions that you talked about are exactly the kinds of things that we want the university to be doing, right? The relationships with industry, and the number of students that you share that come from all over the world to go to school at UW and now are having impact all over the globe. So it's wonderful. And so we're going to open it up to for you to ask questions. I have some, but I'm going to just let others jump in, and you know, feel free to unmute yourself. Don't be shy. This is a conversation, so please, we welcome your contribution.
Well, I'll jump in. Professor Rohatgi and David, really a pleasure listening to both of you. So my question is, you know, there was a lot of talk about metal composites, but how about the plastic composites? What is the future of that, and how does it stack up with regards to metal composites in terms of applications?
Well, I'll start with a couple of comments. First of all, the applications in polymers, I'm going to say there are probably more of them than there are in metals across a broader range of products. And part of that is because it's easier to work with in a polymer versus a molten metal. As Pradeep knows so well, because he's been at our foundry trying to add silicon carbide particles to a 1,000-pound vat of magnesium, there are certain issues with trying to work at those temperatures. And so polymer composites are widely used in sporting goods these days. They are turning more polymers into structural polymers that can be used. It's a little bit of a fundamentally different process, and so they have had they've advanced a little bit faster than we in the metals world have. I think, Pradeep, you may have some additional comments on that as well.
Yeah, I think you're right, Kaushal. The polymer composites are used much more widely. In fact, in many places when I go and you use the word composite, they only think polymer composites. And they have done a great service to humankind. They're used in many applications, but there are limitations. They are not as stiff and as strong as metals, and they cannot withstand high temperatures. So there is a whole lot of applications where you need the ability of a material to withstand high temperatures. And that's where metals are indispensable. Their wear resistance is much better. They don't absorb moisture like polymers do. They don't swell. So in higher performance applications, there is a limit to which you can use polymers. You have no choice but to get to metals. So that's why the metals have been around for many years, even though they consume a lot more energy to make and difficult to handle. And I believe they will remain because there is a fundamental limit to the high temperature capability of polymers because of their nature of the chemical bond. You go above 400 degrees centigrades and there'll be no polymer that can withstand. So that whole range will remain a domain for metals. And when you run out of the properties of single metals like aluminum, then you have no choice but to get to metal composites, which take it to the next higher level. So that's what I see as the place for metal composites in relation to polymer composites, which are very widely spread.
Thank you.
I want to come in with a question, which is a very layperson's question. How will you explain to laypersons what you mean by embodied energy in materials, hmm, as opposed to, let's say, the energy they can emit? And how does this promote what you call a circular economy? I mean, I understand in general what a circular economy is. I suppose even recycling belongs to a circular economy. But I thought you might actually have better, ways of explaining it. This is for both Pradeep and David.
Should I go first, David?
Yeah, go ahead.
Let me give you an example. It takes a lot of energy to make aluminum from the ore. You make a metal, you mine the ore, then you go through a smelting process and you produce an aluminum, and that is then put in your cars or whatever you have. So the energy consumed in this route, where you mine something and then you smelt it and you produce a metal and then you further fabricate it so that it becomes a part of your car. That takes a lot more energy, and they call aluminum has a very high embodied energy. But instead of starting with aluminum that comes out of the ground, if you take aluminum which has a component that has been used and discarded and earmarked for landfill, you take that aluminum, you remelt it, and you do certain science to it, so its properties now are as good as what we call primary aluminum that you made out of the ore. And this process, in case of aluminum, recycling aluminum only takes 10% of energy compared to what you take when you take the ore out of the ground. So in secondary aluminum, the embodied energy is much less. And then I'll give you an example from the field of research that David and I are involved. If I take fly ash is a waste byproduct, and you spend energy in putting it in landfill, and then it ruins your water. If you take that waste material and put it in metals, suppose you are using 1 pound of aluminum, now you displace it and put 20 volume percentage of fly ash. So now the embodied energy of aluminum is only 80% compared to 100%. So the concept of filling a very high energy material with waste byproducts or components with low embodied energy, they will also reduce the embodied energy in materials. So promoting recycling rather than taking materials out from the ground, because we don't have infinite resources. In the ground, the ores will run out. There is a big concern, as you can see, many critical materials or elements that are used for, say, lithium-ion batteries. They come from China, and there could be an instability in their supply. So we need to learn how to recycle this from thrown away iPhones. How do we recover many rare earth materials from thrown away iPhones, from thrown away computers? And not only they recover and conserve resources from the ground, they also have less embodied energy, because it takes much less energy to recycle than to dig something out of the ground and convert into a material.
The other thing that Dr. Rohatgi and I have been looking at is to and he mentioned it a little bit, but to use waste products as the source of your reinforcement in metal matrix composites. For example, in our operation, we're a foundry. We use a lot of sand, but the sand has to be of a certain size. And so if you use the sand that's too small, which we normally landfill, we believe we can use that sand as a way to produce an alumina composite and add silicon to the metal at the same time, cutting out a lot of the embodied energy of the manufacture of a metal matrix composite as well. So there's and the energy savings can be significant when you talk about that. There are a lot of waste sources that can be plant-based or industrial-based that whose materials can be used as reinforcements in composites, and that's another important area.
Well, that's a very useful explanation. Thank you both. Because clearly embodied energy is energy which is captured in the whole process of mining and production, right? And
Right.
then held inside that metal. So yeah, no, that's an amazing thought, because it's both literal and metaphorical and ecological. Thank you.
Uh, Hi, I did, as a layman, I didn't think this subject could be so fascinating. I've always been admired Professor Rohatgi's work, but truly what you talked about today is truly fascinating. A few years ago, I read an article and of course, I was reading it out of just interest, and it said that the Dreamliner was made of composite materials. Is that right? Is it the
Correct, but it was polymer composite.
It's a polymer
Oh,
composite material.
polymer.
It was a
Okay.
polymer composite, and there was an article written that the next generation Dreamliner will be a metal composite. I don't know when that will happen,
Okay.
because when
Because
you want to go still farther, it has to be a metal composite, because there are high temperature parts in an engine. But
Mm.
Dreamliner was a polymer composite.
Yeah, they're high temperature parts. The other issue is repairability, so if you create a big, let's say graphite composite structure and it suffers some damage, it's not a matter of just replacing a panel like you can with an aluminum alloy. And that goes back to the conversation about some of the advantages of metals over polymers. You can do some amazing things and they'll have their place. But I did read the same article that Dr. Rohatgi did, and it was a great idea. It's worked out pretty well for them, but they've been able to fully explore the downside of polymer composites as well, and believe that metal-based composites are going to have improved functionality versus the polymer.
So what about the shipping industry? Is there any use of metal-based composites in that industry?
I'm glad you asked that question. The Navy, of course, likes to reduce the weight of its ships. So they have been talking to us that how you can make ships, instead of big heavy steel, can you make it out of lighter materials, so it can go more more miles to a given fuel. The other thing we are interested in the work, I remember I mentioned the work on self-cleaning materials, where the drag by the water on the ship, can it be reduced by self-cleaning materials and materials that will corrode less. So shipping industry has been talking to us. Right now, as I said, as I speak to you, we are still in the development stage. But Office of Naval Research has funded my work for these reasons. They're interested in reducing corrosion, reducing the weight, and reducing the energy it takes to propel a ship through a mass of water.
I would add that probably there is a reasonably high level of interest from big freight companies, think big Class 8 kind of trucks, the semis that you see on the road every day. They are weight limited. If you open the back of one of those, and I see it every day when they deliver aluminum ingot to us, from a space standpoint, they're less than a third full, because that is all the weight that they're allowed to carry on a highway. So every pound that you take out of that trailer is a pound more freight that they can carry. And this is particularly important with bulk haulers, people who haul liquid. All those trucks that pass you every day are half full at best, because the combined weight of the freight and the truck would exceed what's allowable on the roads if they were running full. And so there's a market there to lightweight that structure so they can pull more freight.
Hi, Dr. Rohatgi and David Weiss. I have a question about the difficulties that you mentioned, and I'm wondering about the following. So one of the things about a new material or a new alloy that you might form would be that that material has to be shaped and cut and formed, right, in different shapes and different formats. And of course, when you build something that's stronger or lighter by mixing the fly ash or graphite and so on, the people who are going to shape it and form it are going to have to be trained differently, and the cutting tools and so on are going to have to be different. I'm wondering what part of the manufacturing chain or the supply chain actually takes care of that part of the research? Who does that?
Question, because he suffers that pain every day. So
yes. So it's a good question, and one of the barriers to the use of composites, and I'm going to say aluminum composites, for example, that contain silicon carbide or alumina, those are hard particles, and one of the barriers, while we can cast those materials almost as inexpensively as we can cast aluminum, oftentimes the machining may be double the cost because of tool wear. There was a lot of research 20 years ago to try to optimize materials, and actually it was very, very good research, and there are commercially available materials that cutting tools that can be used. Part of the problem is education, particularly with an aluminum-based composite. A machine shop gets a part in and says, well, this is aluminum, and they try to run it as they would an aluminum alloy. And you simply can't do that. And so a large part of what we try to do with customers is give them machining guidelines, let them know that it's a different class of material so that they don't fail early in the machining, and just try to flood them with the available literature so they can do it right early, as opposed to getting frustrated by, wearing out tooling after a couple passes. It's one of the barriers, getting that educational content out there to people who are actually going to post-process the composite.
And would you say that this is one of the major barriers of commercializing?
Yes, I would. I would say it's probably the number one barrier, because your customer expects you to complete his supply chain. So if he wants to buy a rotor, he wants to buy a rotor that's machined, and anything else that needs to be done to it. And so it is that machining, because there's not enough people familiar with machining MMCs. Those that do it charge a lot of money for it because they're in demand. And so that is, I'm going to say, you're right to say it is the largest barrier to high performance MMCs for general use, for example, in the automobile industry.
I might add one thing. What David is saying is correct. When you add a hard particle, very hard particle, like silicon carbide and so on, machining becomes difficult. But when you add a solid lubricant particle like graphite, it becomes easier to machine than aluminum. So there is a whole opportunity where, and particularly in automotive sector, where you can use aluminum composites which are easier to machine than aluminum. And they incorporate things like graphite or mica or whatever you have. So not all composites are difficult to machine. There is a whole body of composites that are easier, and you don't have this barrier. And that's why I and David always have this debate that probably they will get into the market first before the hard particle composite gets in.
And is there sufficient research and funding that's coming into that aspect of the chain?
Yes, in machining there has been research, and GE developed polycrystalline diamond as tools. So there is research funding available for machining research.
Thank you.
I just read a headline recently that the world is running out of sand. Is that true?
David will be out of business.
Oh my gosh. Sand is like any other natural resource. There is plenty of sand, but it is getting more and more difficult to extract the kind of sand that people want. One of the things that has happened in our industry, and it was a panic a couple years ago, is sand is heavily used in the fracking industry. And they use sand to help erode the walls of whatever they're digging. Both in that industry and in the foundry industry, there's a huge program for recycling sand. To give you an example, 10 years ago, I'm going to call it 12 years ago. 12 years ago, we threw 100% of our used sand away into landfills, which made it effectively unusable for anything. Today, 98% of our sand is recycled. So in that case, the technology arose actually before the crisis occurred. And so we use very, very little used sand, 1/50th of what we used to use in order to produce the same amount of product. And so wherever sand is being used, the economics of it are such that the price went up because it became more difficult to extract good sand that goaded technologies to recycle it. And so we've reached a happy equilibrium. Just a historical point, Pradeep mentioned earlier about we have as many foundries as any state in the country. And one of the reasons for that is we have two excellent sources of sand. We have the sand that comes from the banks of the Wisconsin River, which continues to be mined in areas for foundry sand. And we have sand from the Lake Michigan beaches as well. They are both some of the finest foundry sand in the world for different applications. So when you wonder why there are so many foundries in Wisconsin, that's one of the reasons. Sand at one point when I started my career was for all effective purposes free, but you just had to pay for the hauling. And so the closer you were to the sand source, the more likely you were to put a foundry there, because the transportation charges were not very high.
You asked a question about sand running out. There are many things that may run out, because a recent article in Nature now said that as of last year, the volume of materials made by mankind, the steel and the cement and the metals and so on, for the first time in human history, that volume is more than the biological materials in the universe. More than the human beings and the plants and everything, animals. So for the first time, man-made materials have exceeded the volume of biological materials, and this could have many implications. One is, of course, you will run out of resources, and that's why emphasis on a circular economy and recycling rather than continuing to deplete materials. Looking at low embodied materials and dematerialization. Can you use for the same function less material? The term that they use is dematerialization. That is coming into being because we just don't have enough resources.
That's right. One of the scary things is that we are going to run out of lithium very soon,
Right.
and cobalt.
And
And
cars may come to a halt.
everything that we use uses batteries, and we might soon come. Yeah, the energy economy might just come to a halt. So any work that is done to alleviate that problem, all the great work that you're doing, not only needs to be supported in the lab, but also what I find is there is not often a support in the entire chain to make it come to market. Right? So many of these good ideas might come up to a point and then never see the light of day.
No, you are very correct. I mean, that's one of the problems. I mean, as I mentioned, I've been very lucky that I was surrounded by industries like Ec Industries, who took the ideas that we generated in lab and at least upscaled it, made prototypes, and made some parts for people. So until the whole supply chain is working with you, many good ideas will just die in the lab.
One of the things, and I'm going to point to an example of what I'm going to call a success story. Ec Industries is part of something called the Critical Materials Institute, which is part of the DOE. And so what they're working on is all aspects of critical materials, recycling, finding new sources of supply. We're involved in it because we're using cerium as an alloying element, and cerium is a little bit like fly ash because it is generally just dumped because cerium as a light rare earth is not used in magnets. But I will tell you, really at the highest levels, there is lots and lots of money flowing out of the government, and they understand the problem. They are subsidizing the development of new resources in the United States. They are subsidizing recycling, and they have made this a joint industry, university, national lab type of program. You don't go forward with something unless you have an industry partner and a national laboratory partner. And so there's a lot of very, very good work going on as far as magnet recycling, other rare earth recycling, different kinds of uses, coal mining with other materials. If you think you're running out of nickel and you have a mine that only has 100 parts per million nickel, how do you recover that 100 parts per million of nickel? So there are lots and lots of work going on because the problem, I'm going to say, is understood at the highest levels of government, and they're going to make sure that we have that critical energy infrastructure going forward.
Well, this is a fascinating discussion, but we are running out of time. I think I feel, to use a colloquial word, quite gobsmacked on many levels, hearing this conversation between the two of you. I mean, one of the things, we are familiar now with recycling and the use of waste and so on and so forth. And, the coconut and bananas are a nice twist in it. But I think what is really interesting here for me, and I speak as a layperson, is that one thinks of pure science as being a particular kind of knowledge, and then applied science as another. And what is fascinating for me, in listening to you, both of you today, is that the implication seems to be that pure science by itself may not be able to be a standalone field of knowledge unless it is working itself into market applications. Now, in the case of both your work, I think that's fantastic because precisely these market applications will help, in various forms of conservation and, maintaining a circular economy. And then I was wondering, is there a non-market arena here that we might gesture at? Not that I expect you guys to answer it, but I was just thinking about it. The second thing I found really even more gobsmacking, because I've only encountered it in science fiction before, is this idea of biomimetic. I love that word, biomimetic, smart self-healing, self-cleaning, and self-lubricating composites, where you have the memory of shape, where you have microballoons. I mean, I know, for instance, that microballoons are being used in retina surgeries now. So, this was, again, really fascinating for me. And I was thinking, since I'm a professor of literature, primarily, but not wholly, that it's amazing how things that come up in science fiction come up in real life quite fast. So that, one has seen, both in science fiction films and in fiction novels, precisely these self-healing, objects and metals, and here they are. They actually are coming into, a whole new arena. What I want to end on doing, which is also a way of thanking you, is to say that today we are, there's a story of two journeys here. The wonderful, absolutely amazing journey that, Pradeep started out with, from sand and ice to, a partnership, between the two of you and other members of the metal industry, the kind of circulation of technology between India and US, which is also actually very much a part of this circular economy, because knowledge here is circling between countries. It goes back, it goes forth, it develops somewhere, it returns somewhere else. So in some sense, there is a kind of alchemical, feeling to this journey. And then the fact that the two of you could come here for this discussion. Now, the second journey is very minor, in a very minor key, which is that Chia and I, in a completely separate conversation, came up with this idea of starting the series of Asia in Conversation. So like Pradeep and David, we are partners in crime too. So I particularly want to end by thanking Professor Pradeep Rohatgi and David Weiss. I want particularly to thank my colleague Shin in women and gender studies, who became the third person in this partnership, widening it and making it more possible. And I also hope that we will be able to continue this series. We have one event lined up for April, and then maybe we'll continue it again next year. We have to consider that. But the event we have lined up is actually a conversation between a Chinese artist, Shitu, and our very own, professor from Women and Gender Studies, Xin Wang. And this will happen in April. And I think what is going to be interesting in this series is that we are going to have widely divergent, topics and partners in conversation, and, probably therefore also, different kinds of audiences each time. So please join me in thanking Pradeep and David again.
Thank you. Thank you for the opportunity.
Thank you for the opportunity.
And put me on your mailing list for the next one, because that sounds tremendously interesting to me.
Well, I'll definitely do that. So hope to meet you all soon in one way or the other, eventually face to face, but for the time being on Zoom.
Okay, very good.
And I'll say good night.
Thank you.
Thank you all.
Thank you.
Thank you. Thank you.
Thank you, Kumkum. Thank you, Chia. Thank you, Zen. And thanks for the audience.
Thanks for organizing.
Thanks.
Thank you. Thank you so much.
Oh, you're welcome, Kaushal.
Yes, great.
It was so good to